In this video, we're going to talk about linear combination and span. So we'll first define what these terms mean and then look at examples to get more comfortable with how to work with them in practice. So here's the definition. Let's let v1, v2, all the way up until vk be vectors in Rn. So that means that each of these vectors has n entries. So let's let c1, c2, all the way up until ck be elements of R. So they're real numbers, they're constants. Then, if I multiply the first vector v1 by c1, and multiply the second vector v2 by c2, and I keep going like that until the last vector vk, I multiply that by ck, and I add all of those together, so I'm sort of multiplying all the vectors by a number, possibly, and then adding them together, that's called a linear combination of the vectors of v1 up until vk. So this whole thing in and of itself is a vector. So a linear combination is a vector. Multiplying vectors by numbers and adding them together, that still gives us a vector. So these numbers, c1, c2, up until ck, they're called the weights of the linear combination. Okay, so the other definition is what's called the span of our vectors. So the span of v1 up until vk. That is all possible linear combinations of the vectors of v1 up until vk. Okay, so first I'll talk conceptually about what this means, and then we'll look at some examples. So conceptually, when we write the span of v1 up until vk, when we talk about all these linear combinations, this conceptually represents everywhere we can get by only traveling. Sorry, let me change one thing about the wording there. This is everywhere that we can get to in Rn by only traveling in the directions of these vectors, v1, comma, dot, 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 up until vk. Okay, so we'll look at an example to see, well, what does that look like in practice? But that is conceptually what span means. Everywhere in Rn, we can get to by traveling in the directions of our vectors. So note that the 0 vector is always in the span of v1 up until vk. At this point, I'd want you guys to pause the video for about 30 seconds and think about why. So 4, 3, 2, 1, pause the video. Okay, so hopefully it's been about 30 seconds for you guys and you thought about it a little bit. So the reason conceptually why is I can always form a linear combination like this that gives me 0. And the way I would do that is I would just do 0 times v1 plus 0 times v2 plus dot 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 plus 0 times the last one, vk. And if I do that, I'm able to attain 0. So because I can write 0 as a linear combination of these vectors, that means 0 is in the span. It's one of the possible linear combinations. Okay, so next let's look at some examples. Okay, so this is example 2. Let's describe the span of the vectors geometrically. So part A of this is I just have one vector, v1, which is 1, 2. So this is 2 entries, which means this lives in R2. Okay, so I want to describe the span of this vector, so the span of v1. So the span is all possible linear combinations of this vector. So this is all linear combinations of v1. So if I'm just taking linear combinations of one vector, that means I could take that vector, v1, and I can multiply it by whatever number I want in front. So I'll just call that number c, so some constant, where c can be any real number. C is an element of the reals. Okay, and if I multiply this vector by a number, I know that what that does is it just scales it. It just scales it and maybe makes it longer, maybe it makes it shorter, or gives it the opposite direction, but it just scales it. So let's draw a picture of that. So let's draw our axes. So our axes, and then 1, 2. So 1 in the x direction, 2 in the y direction. So v1 looks like this. So that's the vector v1. And then when I scale the vector and then multiply it by c, I can get anything, let me put this in green maybe, I can get anything in the same direction of v1, either shorter or longer, or in the opposite direction if I multiply by a negative number. So the span looks like this line. So the span of v1 of this one vector is this line. And notice that this lives in R2. Even though this line, in a sense, is sort of like a one-dimensional thing, it lives in R2, which is two-dimensional. And we'll talk more formally about what dimension means later in the class. Okay, let's do another example. Okay, so we saw the span of just one vector like that gave us a line. What about if I have two vectors? And let's say these two vectors this time are in R3. So v1 is 1, 0, 0, and v2 is the vector 0, 1, 0. So let's take their span. So we have to look at all possible linear combinations of these. So I get to multiply v1 by some scalar, by some constant, I'll call that c1. I get to multiply v2 by some constant, I'll call it c2, and add them together. Let's look at all possible things that this could look like. So I'm multiplying c1 times the vector 1, 0, 0, so times v1. And I'm multiplying the number c2 times the vector v2, which is 0, 1, 0. Okay, and when I multiply a vector, like 1, 0, 0, times this scalar, I multiply the scalar times each of the entries. So c1 is going to distribute into the 1, it's going to distribute to the 0, and it's going to distribute to this bottom 0. And that'll give me c1, 0, 0. If I do the same thing with the next vector, I'll distribute into c2, and I'll get 0, c2, 0. And then finally, now I get to add these two vectors. So c1 plus the 0 at the top entry is c1, 0 plus c2 is c2, and then 0 plus 0 at the bottom is 0. Okay, so any linear combination of these two vectors looks like this. Some number c1 in the first entry, some number c2 in the second entry, and then 0 in the third entry. So what does this look like graphically? So the span consists of all vectors in R3 that have 3 entries that look like this. Well, this is actually just, so if the third entry, this is sort of the zero component, the z component, if the z entry is 0, that means we're talking about the xy plane in 3D space. So we're talking about the xy plane in 3D space. So graphically, if I were to draw, my 3 axes in 3D space, let's say this is x, this is my y, and this is z, we'd be talking about the x and all the vectors that live in just the xy plane. And of course, I could go in the negative directions as well. I've only drawn the positive direction just for simplicity. So there's one important thing that I want to notice about this specific example, which is note that the span of these two vectors, v1 and v2, we cannot say that this is equal to R2. And the reason for that, this is a really common misconception. The reason for that is since the vectors, let me just abbreviate that and say since the vex in the span are in, so all the vectors that we have in the span, so all of these guys, they're in R3. They have 3 entries in them. Even though the last entry is 0, it's there. But when we talk about vectors in R2, they only have 2 entries. There's no third entry in them. So it doesn't make sense to say the span equals R2. As we'll learn later when we talk about dimension, we can say that this span has dimension 2, but it's not the same thing as R2 because the number of entries doesn't match up. All right, so let's end with one more example for this video. So let's say I have 2 vectors again. This time v1 is 1, 3, negative 4. And v2 is the vector 1, 4, 3, 4, and negative 1. So these are vectors in R3 because they each have 3 entries. So let's describe their span. So there's something I want to notice about these 2 vectors and how they're related to each other. You might notice that they are actually multiples. If I v1 is actually 4 times v2. So because of that, when I form any linear combination, so C1 times V1 plus C2 times V2, what I will get is, so I'll write C1, and then for the V1, let's replace V1 with what it equals. V1 is 4 times V2. Whoops. Not an exponent. V2. Okay, so that's what V1 is. And then I still have C2 V2. And now what I can do is, both of these have a V2 in them. So I can factor that out to the right. So I'll factor out V2, and then in front I'll write all of the constant terms. So I have 4C1 plus C2 sort of in the front. And this whole thing in parentheses, this is a constant. So what we're noticing here is when we form any linear combination of our two vectors, it always ends up being just some multiple of V2. So our span, the span of V1 and V2, it always ends up being just a multiple of V2. So in this example, actually, our span is actually just the same thing as the span of V2, because we ended up just reducing our linear combination to being a multiple of just V2 alone. And we know that the span of one vector, as long as that vector isn't a zero vector, the span of one vector on its own is, it's a line, like we saw in part A. It's a line through the origin and V2. And V2 is 1/4, 3/4, -1. So it's really similar to what we got in part A. We always ended up with a multiple of just one vector, and visually that looks like a line through the origin.